So welcome. This is the presentation for the end-to-end object detection with transformers. This paper came from Facebook AI, and Yuri and I are going to be presenting on this paper. So first of all, what we're going to go through in this presentation is the introduction, where we're going to talk about the main contribution and introduce the paper. We're going to get into the implementation of the paper. We're going to have a small demonstration in Jupyter Notebook. And in the end, we're going to have resources and the links and references that we use to create the presentation. So the paper is called End-to-End Object Detection with Transformers. So object detection is defined as the task of finding all the objects in an image and creating a bounding box for all those objects and classifying them from a predetermined set of classes. End-to-end, this is actually one of the bigger contributions of this paper. End-to-end means that object detection runs in a single shot without auxiliary methods that are used in some other object detection models, such as RCNN. So for example, region proposals, how this works is you have regions in the image in which you believe there could potentially be an object, and then you go inside of those regions and you determine where the object is. And now these region proposals have been moved up and up the ladder as the newer versions of RCNN came out with faster RCNN, but this is still a main part of the RCNN structure. And then the other thing is the non-maximum suppression. This is the problem when you get multiple bounding boxes for one object. And then in the end, you have to do in post-processing, get rid of some of these bounding boxes and only leave the one that's the best suited for this object. So this paper is able to do away with these auxiliary methods and do object detection in a more streamlined approach. Transformers, what is meant by transformers? These are the encoder, decoder with attention mechanisms that have been introduced in the paper, Attention is All You Need. So the original uses of these transformers were in sequence tasks. And if you take one example of such task, let's say language translation, let's say we're trying to translate this sentence that we have here into German. You have multiple instances of this attention. So the first attention is within the input sequence itself. So one example of an attention mechanism would be finding words that actually refer to the same thing. So in this sentence, the animal didn't cross the street because it was too wide. It and street are actually referring to the same thing. So there's going to be a attention correlation between those two words. Then number two, the other attention mechanism is between the input sentence and the decoded sentence, the output sentence. So as we're translating this into German, we also realize that street and Straße, those are both the same word. So there's going to be attention between those two. And then similarly to number one, within the output sequence, you're also going to have an attention mechanism. So in a similar way that it and street, these two words are also referring to the same thing. So it makes sense to try to use transformers in images as well. So you would say that this pixel over here is somehow related to this pixel over here because they belong to the same object in the same way that, you know, this word and this word are related because they actually refer to the same thing. And we're going to go into detail how these transformers actually work a little bit later. So the implementation, this is the architecture slide. So let's say we start with an image. We run this image through convolutions to get C feature maps. We reduce the size of these feature maps to D, and then we collapse the height and width of these feature maps to get a sequence of length h times w, and each element of this sequence is of size D. So now the way you can think about this is just a sequence of positions within the image. So this first vector is encoding this location here, for example, the second one to the right, and so on until you get the entire image encoded by positions. And it's of size D because we had D feature maps previously. So each element of this thing is coming from these feature maps. And then you have these positional encodings, which are just ways of telling the encoder which one of these elements, where in the screen does it actually belong. And then these two things together go into the encoder, which has the attention mechanism. And that produces an output that goes into the decoder, along with these object queries. And now the important thing about the object queries is that there's n of them, and they are responsible for locating objects within an image. So these object queries are trained, and they're all going to be specialized in detecting objects in a certain part of the image. And this n is important because n is actually limiting the number of objects that we can have in the image. So in this case, let's say n is 4, we would only be able to detect 4 objects in the image. So this serves as the positional or type of a positional encoding for the decoder. And these values are trained, right? So this is going to change based on your training set. And then what comes out of the decoder is, again, n objects. And then we run those n objects through a feed-forward neural network. And then what comes out of that is a combination of the bounding box and a class for each one of these objects, with no class being one of the valid options, because actually most of the time you're not going to be using all n of your object queries, because n is usually taken to be 100. So actually most of the time you're going to have empty classes and empty bounding boxes. And then the next step is to use this bipartite matching loss to figure out how correct your prediction was. And basically the paper divides these regions into, this part is called the backbone, this is the encoder, the decoder, the prediction heads, and this is the bipartite matching loss. And now we're going to go into detail of how the bipartite matching loss works. So let's say this is the ground truth with the labels, and this is what you predicted. The first issue that you have is that the set of predictions that you have from the ground truth and the predicted set are not the same length, but that can be fixed easily. So you can just add, you can pad up until the end, the set from the ground truth. And now the task is to figure out which one of these elements in the ground truth is to which one of the predicted ones it's referring to. So you kind of want to say that this bird right here, the bounding box for it is the bounding box for this bird right here, to be able to calculate the loss properly. So one way you could do that is take the loss between each one of the elements. And the loss that we're calculating here is just a combination of the box loss and the class loss. So let's say you predicted that this is a bird and this is a bird as well, but your box is slightly off as we have here, you're gonna have a smaller loss. But if you predicted that this was a dog and this was actually a bird, you're gonna have a larger loss. So then you can calculate the loss between all of these elements. But if you were to do that for every one of the elements, the issue is that because there's 100 elements in both of these sets, that would be 100 factorial. So that would be nearly impossible. So you need to find some way to find these matchings in a smarter way. And what you use is this Hungarian algorithm that allows you to find the loss, the optimal loss for these two sets, where the total loss is calculated as just the sum of all the losses of the matched objects that you detected. So now Yuri is gonna take over.
Yeah. Thank you, Marco. So returning to the structure. So let's take a deeper look in, for example, this block positional encoding. So what is actually positional encoding in NLP? It is just an additional vector that you add to your word embedding. So, and it just tells position of the word in the sentence. Here we just can see it embedding and plus positional, and we have embedding with time signal. Speaking about images, in images, it's called spatial signal because it's referred to position of pixels. So here's an example of embeddings with words. And here, for example, an example of image. And here we have image such a size. And after a convolutional neural net, we just have a feature map with smaller size. And our positional encoding corresponds to pixels like that. So, and now talking about transformer. So as input, transformer takes some of positional encoding plus these features. And but what is inside? And it consists of these blocks. So multi-head self-attention, normalization, and feed-forward neural network, and again. But the main magic is done in this block, in self-attention block. So let's take a look inside. So actually, so what we can see here, the same embeddings for these words, thinking, and machines, and we have queries, keys, and values. And these vectors, they just created by multiplying these matrices on these embeddings. So like x1 multiplies by w will be q1. And the main idea, the main magic of attention, that these matrices are learned during the training process. So these matrices kind of pay attention and they focus on different attention and correlation between words. And yeah, and after calculating all these queries, keys, and values, so we can calculate actually our attention score. So first of all, we just multiplying queries vectors on keys vectors and get value. And after that, we divide this value by square root of length of these vectors. This picture corresponds to a particular architecture of transformer, and length of queries and keys and values vectors are 64. That's why we divide by 8, because square root of 64. And yeah, it depends on architecture. But after that, we just take softmax and multiply the softmax on our values. And we have kind of weight, and by the way, pay attention that here we're multiplying to calculate score, we'll multiply Q1 on K1, but here Q1 on K2. So we're multiplying the attention for this word for itself and for word machines. And we do this for every word. And after that, we just adding all these weighted values to vectors, and we have final attention vector. But yeah, so this is how it can looks like attention. And for example, what it does, it takes it looks at hooves and in ears, and it's kind of there is a large correlation between them, and it can say that it is zebra because of these features. And okay, but on the plot you saw that we had multi-head attention. So actually, what is it? It is just the same self-attention, but we have multi-set of matrices. We have a few set of matrices. It trains longer, but we have kind of better results. And the main idea of this, people usually do it. When you have one model, you just take assembly of these models and you have better results. But yeah, but actually what it does, it kind of focuses on different relationships, on different questions. So for example, we have a sentence: the animal didn't cross the street because it was too wide. So cross, and for example, first head focuses on question cross what street, and we have kind of high correlation between cross and street. But another head attention can focus on another question, like who crossed the street, animal. So this is how kind of different head attentions works, multi-head attention. So okay, next. Marco has already talked about that. It's just visualization of one map from the one map from our input. So yeah, as he said, it corresponds to some area on our image and all features from this area. So it can be feature map, so it can be different age, different curves. So yeah, this is how it looks like. Okay, so we have talked about positional encoding. We have talked about transformer, and so encoder, and let's talk about decoder. If we take a look inside, we can see that it's actually is the same as encoder. We have the same multi-head attention. We have the same blocks, and as input, it takes encoder output and object queries. And actually, the main magic also is done by using these object queries. And what are they? So as Marcus said, we have constant amount of elements in these queries. And what they do, they kind of focuses on different parts of the image, and they request different objects, different size of objects. For example, small objects on the bottom, left bottom of the image. So let's take a look at the example. This plot is just points correspond to middle point of bounding boxes of Coco dataset, and green points correspond to small bounding boxes, and red points correspond to big bounding boxes. So, and every element in this query corresponds to an image. So for example, this red square asks for like, okay, it looks at the image and asks, give me all small objects on the left bottom. And the same with this one, like it searches for small objects in the middle of the image. And actually, there, but by the way, I forgot to mention, there also, we learn them during the training process. And it is very important to have to have kind of wide data set, because if we don't have some, for example, if we have data set with only images with bounding boxes in the middle of image, we won't be able to pay attention on different sides. So we'll have to have a balanced data set. Okay, so we have talked about decoder, so let's talk about prediction heads. Actually, there is not much about that. It's just a three-layer pedestron, and the main feature that we have here is kind of have two heads, because one head predicts the bounding boxes, so coordinates, and another head predicts the labels. And yeah, so as this is transformer methods, we have attention, and we can visualize this attention heat maps. And as you can see, it does it quite properly and quite clear. For example, these two cows, they're occluded, but when it pays attention on really every cow separately. So it does it quite clean. And basing on these attention maps, they said, okay, we can make segmentation by just a little bit changing our model, adding segmentation head in the end of the model. And yeah, and it will work fine. So what they did, they had image, they just applied the same attention mechanism, and here they have attention maps, small attention maps, and they pass it through a convolutional neural network. But this is kind of reversed one, because from small images we make big images, bigger one, and here as a result you can see this attention maps, and they're already segmented. So we have only to classify every pixel, and that's why it works kind of clear. You can see, yeah, all edges. Here's just more examples how it works. Yeah, and next, Marco is going to show you Google Colab code implementation of this paper.
Okay, so the first thing that we want to do is check how these models are doing. So one of the main claims of the paper was that it's comparable to FRCNN. So we just put in the FRCNN and the detection transformer model, and we fed it one of the images that we've been using in the video summarization group. because it doesn't belong to the COCO data set. It wasn't trained on. So let's see how it generalizes. And we only select the people. So what you see in this top image, this is the detection transformer. So it actually works pretty nicely. It gets most of the detections, but so does FRCNN. Interestingly, this person is not picked up by the FRCNN, but it's picked up twice by the detection transformer, which is kind of ironic because the detection transformer got rid of non-maximum suppression, but this is exactly like the moment where non-maximum suppression would have told you that this is a double bounding box. Then let's take a look at a couple of other examples. So one of the issues with the detection transformer is small objects. They make this claim even in the paper. And so what you're seeing here happening is not that you're limited by the N that we talked about. It's not that there's more than 100 detections here. There's actually significantly less than 100 detections. But what's happening is that the attention mechanism is not able to contribute much because of all these objects are so small. Because if you remember, when we run this through a convolution, the smallest unit of measure goes from 1 pixel to being 32 pixels. So now, like if you imagine 32 pixels here, there's not much attention that can be going on in areas of more than 32 pixels. So the attention mechanism is not contributing as much. And that's why FRCNN gets significantly more detections. But they provide another version of the model that changes the stride. So instead of taking a look at 30 or changing to 32 pixels, we can change it to 16. So now the attention mechanism is actually able to look at least a little bit more in the local parts of the image, and we do end up seeing a lot more detections. So that's one thing. And then one more thing that I wanted to show you is what happens when we put in the opposite situation. So what happens when we put in a really large object? And that's kind of the bread and butter of detection transformer. Right, so it's completely able to realize, okay, all these pixels over here and all these pixels over here are related. They belong to one bicycle, and this is just one detection, right? And this is where FRCNN struggles. It detects multiple objects for no reason. And then just one more thing that you should pay attention is how long it takes these models to run. So this function is just going to run this thing 3 times and show you how long each one of those things took to run. And while that's going on, let me show you. So we've done the segmentation. We wanted to make sure that it also works for other example, not just in the COCO. So again, we put in our image. And yeah, these are selecting only for people. So as in the paper, it's working quite nicely. And this is what we get as output. This is a pretty clean segmentation of the whole process. And all of these notebooks are available. We posted our notebooks, but they're also all available through the notebook that they, or not the notebook, but the whole repository that they provide. So just looking at some of these numbers, the detection transformer simple model, 3.5 seconds per loop. So 3.5 seconds to run one image. This is without a GPU. The bigger one, it took 6 seconds, so almost double the time as this one, which makes sense, right? Because you reduce the stride, so you're increasing the computation twofold. And then FRCNN is kind of sitting between, still a lot longer than the detection transformer. So in conclusion, if you have big objects, you should go with this small one. It's going to work fine. If you have small objects and you want to use the detection transformer, use the bigger one, but it's going to take longer. And then if you're kind of in between, FRCNN is still competitive. It's definitely by no means that the detection transformer has beat it out completely. So yeah, that's about what we had for the presentation. And here at the end of the presentation, you can see the links to the paper, to the big papers that were cited, and to the notebook that we just shared. So that's the presentation. And if you guys have any questions, feel free to ask questions.